And now let's discuss logarithms. So logarithms are inverse functions to exponentials, and that's sort of their main property, and where all their results come from is the fact that they are inverse functions to the exponential function. What that means is that we say that log base a of x equals y if this is the inverse to the exponential, that is, if a to the y equals x. This is the exponential function with base a. Its inverse is the logarithmic function of base a. Now, for this to make any sense, I need to have a bigger than 0, otherwise the exponential is not defined, so the log isn't either. But I also need it to not be 1. And why is that? That's because the exponential of base 1 is just always 1, and so it doesn't have an inverse because there's no way to get a single output from that because everything is just 1 all the time. Now, what do we know about the exponential function that can help us define things about the logarithm? Well, we know that a to the y is always positive, no matter what a is, assuming a is bigger than 0. So that means that the domain of this function must just be x positive, because otherwise I can't write the expression over here. So since a to the y is always positive, the domain of log a of x is all values of x that are positive, and the range is all real numbers because I can plug all real numbers into the exponential function. Now, there's one particular base that's really nice for logs, and that is log base e. So log base e of x, where e is defined in many different ways. It's like 2.718, and there's a lot of ways to define it that we'll get into a little bit later this semester with how it's defined using calculus. But this is called the natural logarithm, and is often written ln of x, or natural log of x. We'll see this function make an appearance throughout the semester, as it is a really nice function that has certain really nice properties based in calculus. Other logarithms are a little more complicated, but this one is really nice in terms of how it behaves. So what sort of properties do logarithms have? Mostly based on the fact that they are the inverse to the exponential function. So the big ones are things like multiplication. So if I have log, and I'll just write log here, but it applies to any base that I want to use. Log of, say, x times y. This is log of x plus log of y. What you can relate this to is the fact that a to the x plus y is the same as a to the x times a to the y. So multiplication and addition kind of swap roles when you go with logs and exponentials. They sort of interchange how they relate addition and multiplication. The same goes for division. Right? Log of x over y is log of x minus log of y. The other big one here is powers. Log of x to the y, this power gets to jump down in front. So it's y log of x. Again, connected to the fact that a to the x to the y is a to the xy. Products become nested functions here. Again, key mistake warning, addition does not work inside logs. Log of x plus y does not simplify. There's not really much else you can do here. And the last that tend to cause people issues with this are the inverse function relations. These are the relations that look like log base a of a to the x and a to the log base a of x. In both cases, these are x. The first one seems pretty straightforward because that's how the logarithm is defined. That's the properties of the logarithm. The second one looks strange. But if you recognize that what you have here is the function a to the y with y equals log base a of x, you have a function that you're composing with its inverse function. And so you're just going to get x back. Another approach is to think about this in terms of undoing the logarithm again. What does this expression mean? This means that a to what power equals x, if I put, say, I don't know what this is, so I'll call it y. This tells me that log base a of y must equal log base a of x, which means that y equals x, and so this expression actually evaluates to x. Those can be a little trickier to see when they come about, but the main thing to keep in mind is the A's here must match for this to make any sense. If there's anything else going on with the A's or out in front here or inside of here, this relation does not work. It must be just the A's where they sit for this to hold and give you the proper inverse function relations for logs and exponentials.